The Big Bang Theory stands as one of the most fundamental explanations for the origin of our universe. For nearly a century, it has shaped our understanding of cosmic evolution. Taught in classrooms worldwide and celebrated as one of science's greatest achievements, the theory proposes that approximately 13.8 billion years ago, everything in existence emerged from an infinitesimally small, incredibly dense point that suddenly expanded at extraordinary speeds, creating space, time, matter, and energy in one singular event. This elegant framework has guided astronomical research, predicted cosmic phenomena, and offered humanity a compelling narrative about our cosmic origins. Yet beneath this seemingly settled science, a growing number of physicists, cosmologists, and astronomers are raising fundamental questions about the Big Bang's validity. These aren't fringe theorists or scientific contrarians seeking attention. They represent established researchers from prestigious institutions who have spent decades working within the Big Bang framework itself. Their concerns emerge not from philosophical objections but from accumulating observational evidence that increasingly challenges the theory's core predictions. Telescopes of unprecedented power are revealing galaxies that appear to mature, to massive, and too structured to exist in the early universe as the Big Bang model describes it. Measurements of cosmic expansion rates are producing conflicting results that refuse to reconcile despite years of refinement. The universe's large-scale structure displays patterns that demand explanations beyond what conventional theory can provide. The James Webb Space Telescope, launched with great anticipation to peer deeper into cosmic history than ever before, has instead delivered images that confound expectation. Galaxies observed from epochs supposedly just hundreds of millions of years after the Big Bang display characteristics that should have required billions of years to develop. They contain vast quantities of heavy elements, possess well-defined spiral structures, and show evidence of multiple generations of stellar evolution. According to standard Big Bang cosmology, these features represent impossible contradictions, yet they appear consistently across numerous observations. The telescope designed to confirm our understanding of cosmic origins is instead generating data that demands fundamental reconsideration. The expansion rate controversy, known technically as the Hubble tension, has evolved from a minor measurement discrepancy into a full-blown crisis in cosmology. To completely independent methods for measuring how fast the universe expands produce results that differ by approximately 9%. This might sound trivial, but in precision cosmology, this gap represents a chasm. Years of increasingly sophisticated measurements have only sharpened the contradiction rather than resolving it. The possibility that both measurements are correct but our underlying cosmological model is wrong has moved from speculative consideration to serious scientific discussion. Beyond these specific challenges lies a broader philosophical concern. The Big Bang Theory relies heavily on concepts that have never been directly observed or experimentally verified. Dark matter and dark energy together comprise approximately 95% of everything in the universe according to the Standard Model. Yet neither has ever been detected despite decades of increasingly sensitive experiments. These invisible components were introduced specifically to make observations match theoretical predictions. Their continued elusiveness raises questions about whether we are patching an inadequate theory. Rather than confronting fundamental problems with our cosmological framework, the situation resembles other moments in scientific history when accumulated anomalies eventually demanded revolutionary change. Before Einstein's relativity, physicists attempted to preserve Newtonian mechanics through increasingly elaborate modifications. Before plate tectonics, geologists proposed ever more complex explanations for continental shapes and fossil distributions. Before quantum mechanics, classical physics was extended with auxiliary hypotheses to explain atomic behavior. In each case, the scientific community eventually recognized that minor adjustments could not address fundamental inadequacies. The framework itself required replacement. Alternative cosmological models that once seemed highly speculative are receiving renewed attention and development. Cyclic universe theories propose that cosmic history consists of repeated expansion and contraction phases rather than a single beginning. Steady-state models, thoroughly rejected decades ago, are being reconsidered in modified forms that address previous objections. Plasma cosmology, which emphasizes electromagnetic forces on cosmic scales, offers different explanations for phenomena attributed to dark matter. Quantum cosmology attempts to apply quantum mechanical principles to the universe's earliest moments, potentially eliminating the need for a singular beginning point. None of these alternatives has achieved consensus support, but their increasing prominence in serious scientific discourse indicates growing dissatisfaction with conventional theory. The controversy extends beyond technical debates among specialists. How we understand cosmic origins influences fundamental questions about existence, causality, and our place in the universe. If the Big Bang Theory requires substantial revision or replacement, it affects not just cosmology but our broader conception of scientific knowledge itself. It demonstrates that even our most celebrated theories remain provisional, subject to revision when confronted with new evidence. This perspective encourages intellectual humility and openness to radical reconsideration when observations demand it. The evidence challenging the Big Bang comes from multiple independent sources using different methodological approaches. It cannot be dismissed as measurement error, instrument malfunction, or interpretive bias. The problems are systematic, persistent, and growing more pronounced as observational capabilities improve. The scientific community faces a choice between defending an increasingly strained theoretical framework and entertaining the possibility that our most fundamental cosmological assumptions require reconsideration. This choice will define the next chapter in humanity's quest to understand cosmic origins. The Standard Model under scrutiny. The Big Bang Theory achieved dominant status in cosmology during the mid-20th century through a combination of theoretical elegance and observational support. Edwin Hubble's discovery that distant galaxies recede from us at velocities proportional to their distance provided early evidence for cosmic expansion. If the universe is expanding, extrapolating backwards suggested all matter once occupied an extremely small volume. The detection of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson supplied crucial confirmation. This faint microwave glow permeating all space matched theoretical predictions for radiation left over from an early hot, dense state. These discoveries elevated the Big Bang from speculative hypothesis to accepted scientific framework. The theory's mathematical foundation rests on Einstein's general relativity equations applied to the universe as a whole. These field equations describe how matter and energy curve spacetime, producing the gravitational effects we observe. When Alexander Friedmann and Georges Lemaître independently applied these equations to a homogeneous, expanding universe in the 1920s, they found solutions describing a cosmos that originated from a singular point. The mathematics seemed to demand a beginning, a moment when space-time and matter emerged together from conditions of infinite density and temperature. This cosmic singularity, though physically problematic, became central to Big Bang cosmology. The theory's predictive successes reinforced confidence in its validity. It successfully predicted the cosmic abundance of light elements like hydrogen, helium, and lithium formed during the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. The predicted ratios matched observed cosmic abundances remarkably well, providing strong evidence that the universe indeed passed through an early hot phase when nuclear reactions could occur. The theory also predicted the cosmic microwave background's temperature, spectrum, and uniformity with impressive accuracy. These confirmations convinced most scientists that the Big Bang framework correctly described cosmic history. However, the standard Big Bang model required significant modifications to address internal problems that became apparent through the 1970s. The horizon problem questioned how regions of the universe separated by distances greater than light could have traveled since the Big Bang possessed nearly identical temperatures. If these regions could never have been in causal contact, how did they reach thermal equilibrium? The flatness problem noted that the universe's geometry appeared remarkably close to perfectly flat, requiring extraordinarily precise fine-tuning of initial conditions. The monopole problem predicted vast quantities of magnetic monopoles from early universe physics. Yet none were ever observed. cosmic inflation theory was proposed in the early 1980s to address these problems. This modification suggested that the universe underwent a brief period of exponential expansion during the first fraction of a second after the Big Bang, increasing in size by many orders of magnitude in an incredibly short time. Inflation could explain the horizon problem by proposing that the entire observable universe originated from a tiny region that was in causal contact before inflation stretched it to cosmic scales. It solved the flatness problem by driving the universe's geometry toward flatness regardless of initial conditions. It explained monopole absence by diluting these particles to undetectable concentrations. Inflation became incorporated into the standard cosmological model despite lacking direct observational confirmation or a complete theoretical foundation. The mechanism driving inflation, typically attributed to a hypothetical scalar field called the inflaton, has never been identified or detected. The theory requires extraordinary fine-tuning of parameters to produce the observed universe, replacing the original fine-tuning problems with new ones. Alternative explanations for the same phenomena exist but receive less attention because inflation has become orthodoxy. Its acceptance demonstrates how theoretical elegance and problem-solving capacity can establish scientific consensus even without direct empirical verification. The discovery of cosmic acceleration in 1998 through observations of distant supernovae required another major modification to cosmological theory. The universe's expansion was not slowing down under gravitational attraction as expected but accelerating. This completely unexpected finding demanded the introduction of dark energy, a mysterious component with repulsive gravitational effects that comprises approximately 68% of the universe's total energy content. Dark energy has never been directly detected, and its physical nature remains completely unknown. Multiple theoretical explanations compete without clear observational discrimination between them. Its inclusion in the standard model represents a placeholder for ignorance rather than genuine understanding. Dark matter, introduced earlier to explain galactic rotation curves and galaxy cluster dynamics, constitutes another 27% of cosmic energy density according to the standard model. Despite decades of increasingly sensitive direct detection experiments, dark matter particles have never been observed. Their existence is inferred entirely from gravitational effects on visible matter and light. Alternative theories like modified Newtonian dynamics, which adjusts gravitational laws rather than invoking invisible matter, can explain many of the same observations. The persistence of dark matter as the preferred explanation reflects theoretical inertia and investment in particular research programs rather than definitive empirical resolution. The standard cosmological model thus consists of the Big Bang framework supplemented by inflation, dark matter, and dark energy. Together, these components allow theoretical predictions to match a wide range of observations. However, only 5% of the universe's content consists of ordinary matter and energy that we can directly observe and study. The remaining 95% comprises hypothetical components introduced specifically to preserve theoretical consistency. This situation should inspire humility about how well we actually understand cosmic origins and evolution. The model's success in fitting observations may reflect its flexibility and adjustability rather than fundamental correctness. Precision measurements of the cosmic microwave background by satellites like WMAP and Planck refine the standard model as parameters to remarkable accuracy. These experiments measured temperature fluctuations in the background radiation at different angular scales, revealing information about the universe's composition, geometry, and initial conditions. The resulting cosmological parameter values define what is called the Landis-EDM model, which has become the standard framework for cosmology. The model's ability to fit these detailed observations with relatively few free parameters represents a genuine achievement. However, this success depends critically on inflation, dark matter, and dark energy being correct explanations rather than phenomenological patches. Recent observations from the James Webb Space Telescope and other advanced instruments are revealing phenomena that challenge even this refined standard model. These challenges do not represent minor discrepancies or measurement uncertainties that might be resolved through improved data. They constitute systematic contradictions between theoretical predictions and observed reality across multiple independent lines of evidence. The accumulation of these problems suggests that modifications to the Standard Model may prove insufficient, potentially requiring fundamental reconceptualization of cosmic origins. The mature galaxy problem. When the James Webb Space Telescope began returning its first deep-field images in 2022, the astronomical community anticipated confirming theoretical expectations about early galaxy formation. According to Big Bang cosmology, galaxies in the universe's first billion years should appear small, irregular, and primitive. The first stars would have formed from primordial hydrogen and helium, creating simple stellar populations without heavy elements. Galaxies should have grown gradually through mergers and gas accretion, developing complex structures only after billions of years of evolution. Early galaxies should contain minimal dust, show limited star formation, and lack the massive black holes found in mature galaxies today. The observations revealed something entirely different. Galaxies observed from epochs merely 500 to 700 million years after the Big Bang displayed characteristics associated with much older systems. They possessed well-defined spiral structures, indicating organized rotation and gravitational stability that should require extended formation periods. Their stellar populations included significant heavy element abundances, demonstrating that multiple generations of stars had already lived and died, enriching the interstellar medium through supernova explosions. They harbored supermassive black holes containing millions or billions of solar masses, objects that conventional theory suggests need billions of years to accumulate. One particularly striking example is the galaxy JADES GSC 1320, observed at a redshift corresponding to approximately 330 million years after the Big Bang. This galaxy displays a stellar mass exceeding 100 million solar masses and shows spectroscopic evidence of oxygen and other heavy elements. In the standard cosmological framework, this early existence of such a massive, chemically evolved galaxy is extremely difficult to explain. The time available for star formation, chemical enrichment, and mass assembly appears insufficient by an order of magnitude. The galaxy's mere existence challenges fundamental assumptions about how structure formation proceeds in the early universe. Similarly problematic is the discovery of massive galaxy clusters at redshifts previously thought impossible. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing hundreds or thousands of individual galaxies embedded in vast clouds of hot gas. Their formation requires the gravitational assembly of enormous matter concentrations over extended timescales. The Standard Model predicts that such structures should not exist in significant numbers until the universe has aged several billion years. Yet observations now reveal mature clusters at redshifts corresponding to less than 1 billion years after the Big Bang, with properties suggesting much longer formation histories than available time permits. The problem extends beyond individual extreme cases to systematic discrepancies in galaxy number densities and mass distributions. Surveys covering large sky areas reveal more massive galaxies at high redshifts than theoretical models predict. The distribution of galaxy masses and star formation rates shows patterns inconsistent with conventional structure formation scenarios. Attempts to modify theoretical parameters within the standard framework produce improved fits for some observations while worsening agreement with others. The systematic nature of these discrepancies suggests fundamental problems rather than isolated anomalies that might be explained through special circumstances or rare events. Theoretical attempts to explain these observations within the Big Bang framework require increasingly contrived adjustments to initial conditions and physical parameters. Some models invoke exceptionally efficient early star formation, converting primordial gas into stars at rates far exceeding anything observed in the present universe. Others propose that initial density fluctuations were significantly stronger than predicted by inflation theory, allowing structure formation to proceed more rapidly. These modifications generally lack independent theoretical motivation and appear designed specifically to accommodate problematic observations, rather than emerging from fundamental physical principles. The presence of heavy elements in early galaxies creates particular difficulties for standard models. Elements heavier than helium form inside stars through nuclear fusion, then disperse into the interstellar medium when massive stars explode as supernovae. This process requires at least one complete stellar generation to produce significant heavy element abundances. Massive stars that produce the most heavy elements live only a few million years before exploding, but their death must be followed by new star formation incorporating the enriched material. This multi-stage process takes time that simply does not appear available in the Big Bang timeline for the earliest observed galaxies. The supermassive black hole problem compounds these difficulties. Current theoretical understanding suggests black holes grow through two main mechanisms: accretion of surrounding material and mergers with other black holes. Both processes have fundamental rate limits. Accretion cannot proceed arbitrarily fast because radiation pressure from the infalling material eventually counteracts gravitational attraction. A limit known as the Eddington rate, growing a billion solar mass black hole through accretion at the Eddington limit, even starting from a stellar mass seed black hole, requires hundreds of millions of years. The discovery of such massive black holes at redshifts corresponding to less than 700 million years after the Big Bang leaves insufficient time for their growth. Through conventional mechanisms, alternative black hole formation scenarios have been proposed to address this timing problem. Some suggest that supermassive black holes form directly from collapsing gas clouds in the early universe rather than growing from stellar remnants. This direct collapse mechanism could create massive seed black holes that would require less time to reach observed sizes. However, this scenario faces its own difficulties, including the question of what prevents the collapsing gas from fragmenting into stars rather than forming a single massive black hole. The conditions required for direct collapse appear quite special and may not occur frequently enough to explain the abundance of early supermassive black holes. The dust content observed in some early galaxies presents another challenge to conventional timescales. Dust grains, consisting of silicates, carbon, and other heavy elements, form primarily in the outer atmospheres of evolved stars and in supernova ejecta. Significant dust accumulation requires not only heavy element production but also sufficient time for dust grain formation and survival. Some galaxies observed at high redshifts contain dust masses comparable to local universe galaxies despite existing in an epoch when dust should be minimal. This observation demands either extraordinarily rapid dust production or extremely efficient dust formation mechanisms that operate under early universe conditions. The morphological maturity of early galaxies challenges theoretical expectations about galaxy formation mechanisms, according to hierarchical structure formation models based on dark matter simulations. Early galaxies should result from chaotic mergers of smaller systems, producing irregular morphologies. Regular features like spiral arms, central bulges, and stellar disks should emerge only gradually as galaxies grow and settle into stable configurations. The observation of well-organized structures in galaxies existing merely a few hundred million years after the Big Bang contradicts these expectations, suggesting that galaxy formation processes may operate differently than currently modeled, or that the timescales involved are fundamentally wrong. These observational challenges have sparked intense debate within the cosmological community about their implications for the Big Bang framework. Conservative interpretations suggest that our models of galaxy formation and evolution require refinement, but that the basic Big Bang timeline remains sound. More radical perspectives argue that the systematic nature of the discrepancies indicates fundamental problems with the cosmological framework itself. The discovery of mature galaxies in the supposedly primitive early universe represents perhaps the most direct observational challenge to Big Bang chronology, raising questions about whether cosmic history actually follows the timeline the theory describes. The Hubble tension crisis. The Hubble constant represents one of cosmology's most fundamental parameters, quantifying the universe's current expansion rate. Its value determines cosmic age, size, and the evolution of structure formation throughout cosmic history. For decades, measuring the Hubble constant with increasing precision has been a central goal of observational cosmology. Two entirely independent measurement methods have been refined to exceptional accuracy, yet they produce results that disagree significantly. This discrepancy, known as the Hubble tension, has evolved from a curiosity into a crisis challenging the foundations of standard cosmology. The first method, called the distance ladder approach, uses observations of relatively nearby astronomical objects to build up distance measurements in a stepwise fashion. The process begins with geometric distance measurements to nearby stars using parallax, the apparent shift in stellar positions as Earth orbits the Sun. These direct geometric measurements calibrate the luminosity of Cepheid variable stars, which change brightness in regular patterns related to their intrinsic luminosity. Observations of Cepheids in more distant galaxies then calibrate the peak brightness of Typeus supernovae, which serve as excellent standard candles for measuring distances to extremely remote galaxies. By measuring how fast these distant galaxies recede from us and knowing their distances, the Hubble constant can be calculated. The most precise distance ladder measurements, led by the SHOES project using Hubble Space Telescope observations, determine a Hubble constant value of approximately 73 kilometers per second per megaparsec. This means that for every megaparsec of distance, galaxy recession velocities increase by 73 kilometers per second. The measurement precision has improved dramatically through extensive observational campaigns and sophisticated analysis techniques. The uncertainty in this value has been reduced to less than 2%, making it one of the most accurately determined cosmological parameters. The result has remained stable across different analysis approaches and independent research teams, increasing confidence in its validity. The second method derives the Hubble constant from observations of the cosmic microwave background radiation combined with the standard cosmological model. The Planck satellite mapped temperature fluctuations in the cosmic microwave background with unprecedented precision, measuring variations at different angular scales. These patterns reflect acoustic oscillations in the primordial plasma that filled the early universe. The physics of these oscillations is well understood, allowing theoretical predictions of the pattern characteristics given specific cosmological parameters. By fitting the observed patterns to theoretical predictions, the entire set of cosmological parameters including the Hubble constant can be determined. The cosmic microwave background method produces a Hubble constant value of approximately 67 kilometers per second per megaparsec, about 9% lower than the distance ladder result. The precision of this measurement is comparable to the distance ladder approach, with uncertainties also near 2%. The discrepancy between the two values is approximately 5 sigma, meaning the probability that this difference results from random statistical fluctuations is less than 1 in a million. This represents a highly significant disagreement that cannot be dismissed as measurement noise or systematic error affecting one method. Both approaches have been scrutinized extensively, and both appear robust. Attempts to identify systematic errors in either measurement method have proven unsuccessful. The distance ladder approach has been questioned regarding the calibration of Cepheid distances, potential contamination of supernova samples, and the effects of local large-scale structure on velocity measurements. Extensive testing has failed to identify problems sufficient to explain the discrepancy. Similarly, the cosmic microwave background analysis has been examined for potential systematic effects related to foreground contamination, instrumental systematics, and theoretical modeling assumptions. Multiple independent analyses using different computational approaches and datasets have confirmed the Planck results, making systematic error an unlikely explanation. The persistence of this tension across multiple independent measurements and analysis techniques suggests that the problem may lie not in observational systematics, but in the cosmological model itself. The cosmic microwave background method assumes the standard lambda-CDM cosmological model to convert observed temperature fluctuations into parameter values including the Hubble constant. If the underlying model is incorrect or incomplete, the derived Hubble constant would be systematically biased. The distance ladder method is more model independent, relying primarily on geometric principles and empirical calibrations. This difference suggests that the cosmic microwave background result might reflect model inadequacy rather than measuring the actual current expansion rate. Several theoretical modifications to the standard model have been proposed to resolve the Hubble tension. Early dark energy models suggest that a component with dark energy-like properties existed in the early universe, modifying the expansion history in ways that affect the relationship between early universe observations and the present Hubble constant. Extra-relativistic particle species in the early universe could alter the physics of the cosmic microwave background era, shifting parameter values extracted from the data. Modifications to the properties of dark matter or neutrinos have been explored as potential solutions. Each of these proposals introduces new physics beyond the standard model, representing theoretical speculation rather than observationally motivated extensions. None of the proposed solutions has achieved consensus support within the cosmological community. Most modifications that successfully reduce the Hubble tension worsen agreement with other observations or introduce new theoretical problems. For example, early dark energy models that resolve the tension often predict more small-scale structure than observed or require extraordinarily precise fine-tuning of parameters. Modified dark matter properties that address the Hubble tension frequently conflict with constraints from galaxy cluster observations or large-scale structure measurements. The difficulty in finding a single modification that addresses the tension without creating new problems suggests the issue may be more fundamental than a missing component or incorrect parameter value. Some cosmologists have begun considering more radical possibilities, including that the lambda CDM framework is fundamentally inadequate. If the basic assumptions underlying the standard model are incorrect, no amount of parameter adjustment or minor modification will successfully reconcile different observations. This perspective remains controversial because the lambda CDM model successfully fits an enormous range of cosmological data from multiple epochs and physical scales. Abandoning or drastically modifying this successful framework would require compelling motivation. The Hubble tension, while significant, represents a single major discrepancy. However, when combined with other observational challenges like the mature galaxy problem, the case for fundamental reconsideration becomes stronger. The implications of the Hubble tension extend beyond technical cosmology to fundamental questions about the nature of scientific knowledge. The situation demonstrates that high-precision measurements do not necessarily produce consensus if the underlying theoretical framework is problematic. It shows that systematic model dependence can affect derived quantities even when observational data are extremely accurate. The crisis illustrates how theoretical assumptions become embedded in what appear to be direct empirical measurements. For the cosmic microwave background method, the Hubble constant is not directly observed but inferred through a theoretical chain connecting all universe physics to present-day expansion rates. If any link in this chain is incorrect, the final result will be systematically wrong regardless of observational precision. The Hubble tension has created an unusual situation in cosmology where different camps favor different Hubble constant values based on which measurement method they trust more. Distance ladder proponents emphasize the model independence and empirical grounding of their approach. Cosmic microwave background supporters point to the extraordinary precision and physical depth of early universe observations. Both perspectives have merit, and the inability to definitively resolve which is correct after years of intensive effort suggests that the standard framework may lack the capacity to consistently describe observations from different cosmic epochs. The persistence and even strengthening of the Hubble tension as measurement precision improves contrasts sharply with typical scientific experience, where better measurements usually resolve discrepancies by revealing that one method contained systematic errors. Instead, improved measurements have sharpened the disagreement, increasing confidence that both methods are accurately measuring something but that the cosmological framework connecting them is inadequate. 8. This pattern resembles historical situations where accumulating precision measurements eventually reveal fundamental theoretical problems, requiring new frameworks that could consistently explain all observations. Dark matter's continued elusiveness. Dark matter represents one of the most profound mysteries in contemporary physics. The concept emerged from observations that visible matter alone cannot account for gravitational effects observed on galactic and cosmic scales. Galaxy rotation curves, which plot orbital velocities of stars and gas as functions of distance from galactic centers, remain flat far beyond visible matter distributions rather than declining as Newtonian gravity would predict. Galaxy clusters contain far too little visible matter to prevent their constituent galaxies from flying apart given their observed velocities. Gravitational lensing observations reveal mass distributions that greatly exceed luminous matter. These and other phenomena led to the hypothesis that the universe contains roughly 5 times more dark matter than ordinary matter. The standard cosmological model attributes dark matter to undiscovered elementary particles that interact gravitationally but not electromagnetically, making them invisible to telescopes. These hypothetical particles, generically called weakly interacting massive particles or WIMPs, would have been produced in enormous quantities during the Big Bang's early moments. They would have clumped under gravity, forming the scaffolding around which ordinary matter accumulated to form galaxies and larger structures. This dark matter framework has become fundamental to understanding structure formation in the universe. Computer simulations incorporating dark matter successfully reproduce many observed features of cosmic large-scale structure, providing theoretical support for the concept. Despite dark matter's central role in cosmology, direct detection attempts have consistently failed. Experiments placed deep underground to shield against cosmic ray interference have searched for dark matter particles colliding with ordinary atomic nuclei. These detectors use various target materials and detection technologies, achieving sensitivities capable of detecting interactions far weaker than originally anticipated. Decades of increasingly sophisticated experiments have explored vast regions of parameter space without producing confirmed dark matter signals. While occasional excess events generate brief excitement, none has withstood scrutiny as definitive dark matter detection. Particle collider experiments have similarly failed to produce dark matter evidence. The Large Hadron Collider, which discovered the Higgs boson, has searched extensively for dark matter particle candidates through multiple channels. Theories like supersymmetry that elegantly provide dark matter candidates also predict other new particles that should appear at accessible energies. The absence of these signals has progressively constrained and eliminated many theoretically motivated dark matter models. The parameter space available for conventional WIMP candidates has shrunk dramatically, forcing theorists to consider increasingly exotic particle physics scenarios. Alternative dark matter candidates beyond conventional WIMPs have been proposed and tested. Axions, hypothetical ultralight particles originally proposed to solve a different physics problem, represent one leading alternative. Multiple experiments have searched for axions without success. Sterile neutrinos, primordial black holes, and various exotic particle physics models have been explored through dedicated experiments and astronomical observations. Each candidate brings its own theoretical motivation and observational signatures, but none has produced convincing positive evidence. The continued failure to detect dark matter particles despite expanding experimental capabilities raises fundamental questions about whether the particle dark matter hypothesis is correct. Modified gravity theories offer a completely different approach to explaining dark matter-like phenomena without invoking invisible matter. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravitational physics differs from Newtonian predictions in the weak acceleration regime characteristic of galaxy outskirts, with appropriate parameter choices. MOND successfully reproduces galaxy rotation curves without requiring dark matter. The theory makes specific predictions about galaxy behavior that differ from dark matter predictions, and observations increasingly favor MOND in various contexts. However, MOND faces difficulties explaining galaxy cluster dynamics and cosmic microwave background observations, limiting its acceptance. Relativistic extensions of MOND and other modified gravity theories attempt to address these limitations while preserving the theory as successes. Thieves MOND and other frameworks modify Einstein's general relativity in ways that reproduce MOND's behavior in appropriate limits while potentially explaining larger-scale phenomena. These theories remain less developed than dark matter models and face their own theoretical and observational challenges. The broader point is that dark matter is not the only possible explanation for gravitational anomalies, and alternatives deserve serious consideration given dark matter's continued elusiveness. Some observational evidence actually favors modified gravity over dark matter. The Bryonic-Tully-Fisher relation, which connects galaxy rotation velocities to their visible matter content with remarkable precision, is naturally explained by MON but requires fine-tuning in dark matter models. The specific way rotation curves deviate from Newtonian predictions correlates strongly with visible matter distributions in ways that seem coincidental if dark matter dominates. Ultra-diffuse galaxies, which contain little visible matter, should have large dark matter halos according to standard theory but show rotation curves inconsistent with this expectation. These and similar observations suggest that gravitational behavior may fundamentally differ from standard physics predictions rather than resulting from invisible matter. The distribution of dark matter inferred from gravitational observations does not always match theoretical predictions from cosmological simulations. Dark matter simulations predict cuspy density profiles in galaxy centers, where density increases steeply toward the galactic core. Actual galaxies often display chord profiles, where central density remains relatively constant. This core cusp problem has persisted despite attempts to resolve it through boron feedback mechanisms. Similarly, simulations predict many more small satellite galaxies around large galaxies than observed, the so-called missing satellites problem. While various explanations involving gas physics and star formation have been proposed, the problems remain unresolved. The detection of dark matter through its gravitational effects depends on theoretical assumptions about how gravity operates. If gravitational physics differs from general relativity predictions at specific scales or in particular regimes, mass distributions inferred from gravitational observations would be systematically incorrect. The circular reasoning becomes apparent. We infer dark matter as existence because gravitational effects exceed what visible matter should produce assuming standard gravity. Then use this inferred dark matter distribution to validate the standard gravity assumption. If the gravity assumption is wrong, the entire inferential chain collapses. Some physicists have suggested that dark matter might not exist at all, that the phenomena attributed to it actually result from our incomplete understanding of gravity, quantum effects, or emergent phenomena in complex systems. Eric Verleen's emergent gravity proposal, for example, suggests that gravitational attraction emerges from entropic effects associated with information storage in spacetime. In this framework, dark matter-like effects arise naturally without requiring new particles. While highly speculative and facing its own empirical challenges, such proposals illustrate that alternatives to particle dark matter exist and deserve investigation. The philosophical implications of dark matter's elusiveness deserve consideration. Science generally progresses by proposing hypotheses, deriving testable predictions, and confirming or falsifying theories through observation. Dark matter was proposed to explain specific observations, and its particle nature implies testable consequences through direct detection, collider production, or indirect detection via annihilation products. The persistent failure of these tests should, in principle, count as evidence against the hypothesis. Instead, each failed experiment is interpreted as constraining parameter space rather than challenging the fundamental assumption. This pattern resembles the Ptolemaic epicycles added to geocentric astronomy to maintain the theory despite conflicting observations. The investment in dark matter research, both intellectual and financial, creates inertia-resisting alternative explanations. Thousands of researchers have built careers around dark matter physics. Cosmological simulations assume its existence, and interpretation of countless observations depends on the framework it provides. This situation makes objective evaluation difficult because abandoning dark matter would invalidate enormous bodies of work and require fundamental reconsideration of many accepted results. Science is supposed to follow evidence regardless of such concerns, but in practice, paradigm shifts face resistance proportional to the investment in existing frameworks. The dark matter situation demonstrates how theoretical entities introduced to explain observations can become reified through repeated use despite lacking direct empirical confirmation. Dark matter began as a hypothesis, a possible explanation requiring verification through decades of use in theoretical models and observational interpretation. It has achieved the status of established fact in many cosmologists' minds despite never being directly detected. This transformation from hypothesis to accepted reality without definitive empirical confirmation illustrates how scientific knowledge sometimes rests on weaker foundations than commonly believed. Dark energy and the acceleration puzzle. The discovery of cosmic acceleration in 1998 through observations of distant Type Ia supernovae shocked the cosmological community. Two independent research teams found that supernovae at high redshifts appeared dimmer than expected, indicating they were farther away than standard cosmological models predicted. The only explanation consistent with general relativity was that the universe's expansion has been accelerating rather than decelerating. This discovery directly contradicted theoretical expectations based on gravity's attractive nature. Matter and energy produce gravitational attraction that should slow cosmic expansion. Acceleration requires a repulsive force overcoming this attraction. Dark energy was introduced as the mysterious agent driving acceleration. In the standard lambda-CDM cosmological model, dark energy is represented by the cosmological constant, originally introduced by Einstein and later discarded as his biggest blunder when the universe was discovered to be expanding. The cosmological constant represents energy inherent in space itself, maintaining constant density even as the universe expands. This property produces repulsive gravitational effects that can drive accelerated expansion. Dark energy now comprises approximately 68% of the universe's total energy budget, dominating cosmic dynamics despite having no confirmed physical basis. The physical nature of dark energy remains completely unknown, if represented by the cosmological constant. It corresponds to vacuum energy density. Quantum field theory predicts vacuum energy from zero-point fluctuations of quantum fields. But theoretical calculations produce values vastly exceeding observed dark energy density by factors of 1012. This enormous discrepancy, called the cosmological constant problem, represents perhaps the most severe fine-tuning issue in physics. No known mechanism explains why vacuum energy density takes the precise value inferred from cosmic acceleration observations rather than the much larger values theoretical physics predicts. Alternative dark energy models propose dynamical fields rather than a cosmological constant. Quintessence models invoke scalar fields with specific potential energy functions that evolve over cosmic t, producing acceleration in the present epoch. These models add free parameters and require fine-tuning, aim to match observations while offering little theoretical motivation beyond avoiding the cosmological constant problem. Phantom energy models propose energy densities that increase with cosmic expansion, leading to future Big Rip scenarios where expansion accelerates without limit, eventually tearing apart all gravitationally bound structures. These speculative models illustrate theoretical uncertainty regarding dark energy's fundamental nature. Evidence for cosmic acceleration rests primarily on the luminosity-distance relationship measured using Type Ia supernovae. These stellar explosions serve as standardizable candles because their peak brightness correlates with their light curve decline rate, allowing intrinsic luminosity to be determined from observed light curve shape. However, supernova standardization depends on empirical correlations rather than fundamental physical principles. Systematic effects like evolution of supernova properties with cosmic epoch, test extinction, or population differences could potentially mimic the observed brightness patterns attributed to cosmic acceleration. Numerous systematic effects have been investigated as potential explanations for supernova dimming without invoking dark energy. Intergalactic dust absorption could make distant supernovae appear dimmer. Evolution in supernova progenitor populations over cosmic time could affect brightness distributions. Selection effects might systematically bias distance samples. Gravitational lensing by large-scale structure could modify observed brightness patterns. Extensive analysis has examined each possibility without finding sufficient systematic effects to explain observations without acceleration. However, the concern remains that unknown systematics might produce misleading results. Independent evidence for cosmic acceleration comes from baryon acoustic oscillations observed in galaxy distributions. These oscillations represent imprints of sound waves in the early universe that propagated through the primordial plasma before recombination. The characteristic scale of these oscillations provides a standard ruler for measuring cosmic expansion at different epochs. Observations of borean acoustic oscillations at various redshifts reveal expansion histories consistent with dark energy-driven acceleration. While strengthening the empirical case, this evidence still depends on cosmological model assumptions that connect observed galaxy clustering to underlying physics. Cosmic microwave background observations also support dark energy indirectly through constraints on cosmic geometry. The standard Big Bang model without dark energy predicts an open universe with negative spatial curvature. Observations indicate the universe is geometrically flat or very nearly so. Achieving flatness requires total energy density to equal the critical density. Given measured matter density falling short of critical density, additional energy in the form of dark energy becomes necessary to achieve observed flatness. However, this argument depends on assuming inflation drove the universe toward flatness and that geometry measurements accurately reflect underlying cosmology. Alternative explanations for apparent cosmic acceleration challenge the need for dark energy. Some theories propose that we inhabit an unusually low-density region of the universe, creating systematic biases in distance measurements that mimic acceleration. Backreaction models suggest that averaging Einstein's equations over inhomogeneous matter distributions produces effective acceleration without requiring dark energy. Modified gravity theories introduce scale-dependent or time-dependent gravitational physics that produces accelerating expansion through altered gravitational dynamics, rather than exotic energy components. The cosmological constant's value raises profound fine-tuning questions beyond the vacuum energy calculation problem. If the cosmological constant took a value only slightly larger than observed, galaxies and stars could never have formed because repulsive effects would have prevented gravitational collapse of matter. A significantly smaller value would have made dark energy dynamically irrelevant throughout cosmic history. The observed value appears finely tuned to become dominant in the cosmic epoch we happen to inhabit. This apparent coincidence has led to anthropic arguments suggesting we observe a particular cosmological constant value because only universes with such values produce observers. Such reasoning troubles many physicists as abandoning the search for physical explanations. Dark energy's dominance in the contemporary universe but negligible role in earlier epochs creates theoretical puzzles. For most of cosmic history, matter and radiation dominated cosmic dynamics, with dark energy becoming significant only relatively recently. The specific cosmic epoch when dark energy becomes dominant appears coincidental from a theoretical perspective. Why does dark energy transition to dominance now rather than much earlier or later in cosmic history? The lack of compelling theoretical explanation for this timing represents another fine-tuning issue that remains unresolved. Attempts to measure dark energy properties beyond its average density have yielded limited results. If dark energy results from a dynamical field rather than a cosmological constant, its density might vary with time or space. The equation of state parameter relating dark energy pressure to density could differ from the constant value of -1 predicted for a cosmological constant. Observations constrain possible deviations but remain consistent with a cosmological constant. The data lack the precision to definitively distinguish between constant and evolving dark energy, leaving fundamental questions about dark energy's nature unanswered. The interpretation of cosmic acceleration as evidence for dark energy depends critically on general relativity's validity on cosmological scales. General relativity has been extensively tested in the solar system and through binary pulsar observations. But these tests probe strong gravitational fields at relatively small scales, extrapolating the theory's validity to cosmological scales spanning billions of light-years represents an enormous theoretical leap. If gravity operates differently on these scales, observations attributed to dark energy might instead reveal modified gravitational physics. This possibility motivates alternative theories where gravitational attraction weakens at cosmic distances, naturally producing apparent acceleration without exotic energy components. The philosophical implications of attributing 68% of cosmic energy content to a completely unknown entity deserve reflection. Dark energy represents a placeholder for ignorance rather than genuine physical understanding. Its introduction follows a pattern familiar from physics history, where ad hoc hypotheses preserve failing theories by explaining away problematic observations. Before Einstein's relativity, physicists proposed the luminiferous ether to provide a medium for light wave propagation. Before Copernicus, astronomers added epicycles to geocentric models to explain planetary motions. In each case, the solution involved adding unobserved entities to maintain existing frameworks rather than questioning fundamental assumptions. Dark energy might represent a similar situation where conceptual revolution ultimately proves necessary. Alternative cosmological models. Dissatisfaction with Big Bang cosmology's reliance on undetected dark matter and dark energy has motivated development of alternative theoretical frameworks. These alternatives approach cosmic origins and evolution from fundamentally different perspectives, challenging Big Bang assumptions while attempting to explain the same observational evidence. While none has achieved the comprehensive empirical success or broad acceptance of standard cosmology, their existence demonstrates that the Big Bang framework is not the only logically possible explanation for cosmic observations. Examining these alternatives illuminates assumptions underlying conventional theory and identifies which observational facts genuinely constrain cosmological models versus which features result from specific theoretical choices. Steady-state cosmology, originally proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle, posits that the universe has no beginning and maintains constant average density despite expansion through a continuous matter creation. In this model, new matter appears spontaneously in intergalactic space at exactly the rate required to maintain constant density as cosmic expansion dilutes existing matter. The theory embraces the perfect cosmological principle, stating that the universe appears the same from all locations and at all times. This principle eliminates the special status accorded to the Big Bang's unique beginning, replacing temporal evolution with eternal steady state. Steady-state cosmology was largely abandoned following the discovery of cosmic microwave background radiation, which appears naturally explained by the Big Bang's hot early phase but lacks obvious explanation in steady-state frameworks. However, quasi-steady-state cosmology, developed by Hoyle, Jayant Narlikar, and Geoffrey Burbidge, attempts to incorporate this observation through cyclic processes creating bursts of radiation during periodic creation events. The modified theory suggests the universe undergoes oscillations on timescales of tens of billions of years, with matter creation concentrated in brief explosive episodes. These episodes could potentially produce background radiation while preserving the theory's fundamental steadiness over longer timescales. Plasma cosmology emphasizes electromagnetic forces rather than gravity as the dominant organizing principle on cosmic scales. Developed primarily by Hans Alfvén, Nobel laureate in plasma physics, this approach notes that 99% of visible matter exists as ionized plasma rather than neutral gas. Plasmas carry electrical currents and respond to magnetic fields, producing long-range forces that can compete with or exceed gravitational effects. Plasma cosmology explains cosmic structure formation through electromagnetic interactions organizing matter into filaments, sheets, and voids without requiring dark matter. Observations of the universe's large-scale structure do reveal filamentary patterns consistent with electromagnetic self-organization. Plasma cosmology rejects the Big Bang's singular origin, instead proposing an eternal universe evolving through electromagnetic processes across arbitrarily long timescales. The cosmic microwave background is attributed to starlight thermalized through absorption and ray emission rather than primordial radiation from a hot early phase. The theory faces significant challenges explaining detailed features of cosmic microwave background temperature fluctuations and the abundances of light elements, which Big Bang nucleosynthesis naturally explains. Despite these difficulties, plasma cosmology attracts support from researchers who emphasize electromagnetic phenomena's importance in astrophysics and cosmology. Cyclic or oscillating cosmological models propose that the universe undergoes repeated expansion and contraction phases rather than originating from a singular Big Bang. Each cycle consists of an expansion epoch resembling our current universe, eventual contraction driven by attractive forces, and rebirth through a bounce replacing the singular Big Bang. The universe could have undergone infinite previous cycles, eliminating the problem of explaining an ultimate beginning. Cyclic models must address how entropy resets between cycles and what physical mechanism produces the bounce preventing collapse to a singularity. Recent cyclic proposals incorporate ideas from string theory and extra dimensions to address these challenges. The aperiodic scenario, developed by Paul Steinhardt and Neil Turek, suggests that our universe represents a three-dimensional membrane in higher dimensional space. Cyclic evolution results from periodic collisions between our membrane and a parallel membrane. These collisions provide the energy driving expansion and generate density fluctuations that seed structure formation. The model claims to explain many observations attributed to inflation without requiring a singular beginning. However, the theory remains highly speculative, depending on unverified string theory predictions and unobserved extra dimensions. Tired light theories propose that photons gradually lose energy during their journey through space, producing redshift without requiring cosmic expansion. Light energy loss could result from interactions with intervening matter, quantum effects, or intrinsic photon properties. If redshift results from energy loss rather than expansion, the Big Bang framework's foundation collapses. The universe could be static or evolving in ways completely different from standard cosmology. However, tired light faces severe observational problems. Energy loss mechanisms predict image blurring and surface brightness changes that observations do not confirm. Time dilation effects in supernova light curves provide strong evidence for expansion-based redshift rather than energy loss. Quantum cosmology attempts to apply quantum mechanics to the universe as a whole, potentially eliminating the Big Bang singularity through quantum effects. The Wheeler-DeWitt equation represents the universe's wave function, describing quantum superpositions of different cosmic geometries and field configurations. In some interpretations, this framework allows the universe to quantum tunnel into existence from nothing, bypassing questions about what existed before the Big Bang. The Hartle-Hawking no-boundary proposal suggests that time becomes space-like near the Big Bang, eliminating temporal beginning just as Earth's surface has no edge despite being finite. Loop quantum cosmology, derived from loop quantum gravity theory, suggests that quantum geometry effects prevent singularities by introducing a maximum matter density. When density reaches this quantum limit during contraction, repulsive quantum geometric effects produce a bounce, transforming contraction into expansion. This scenario eliminates the Big Bang singularity while preserving many standard cosmology features. The universe could have existed previously in a contracting phase before bouncing into current expansion. However, loop quantum gravity itself remains incomplete and unverified, making cosmological applications speculative. Variable speed of light theories propose that light speed was much greater in the universe's early moments, solving horizon and flatness problems without requiring inflation. If light traveled faster during the early universe, causally connected regions could be much larger, explaining observed uniformity. Light speed decreasing to present values would modify expansion dynamics in ways potentially explaining various observations. However, varying light speed requires modifying fundamental physics in ways that create consistency problems with established theory. Time standards, energy conservation, and other fundamental concepts become problematic when light speed varies. These alternative frameworks share common features worth noting. Most attempt to eliminate the Big Bang singularity either through cyclic evolution, eternal existence, or quantum effects. Many reduce or eliminate dark matter and dark energy by modifying gravitational or electromagnetic physics. Several invoke unverified physics from quantum gravity, string theory, or plasma dynamics to explain cosmic phenomena. None has developed the comprehensive observational support and predictive power that established the Big Bang framework's dominance. However, their existence demonstrates that cosmic observations admit multiple theoretical interpretations, and choosing between them requires careful consideration of empirical evidence and theoretical principles. The relationship between these alternatives and the Big Bang framework is more complex than simple right versus wrong dichotomy. Some alternatives might capture important physical processes that standard cosmology neglects. Electromagnetic effects could play larger roles in cosmic structure formation than currently recognized, while the overall Big Bang timeline remains correct. Quantum cosmology might accurately describe the universe's earliest moments, while standard cosmology correctly describes later evolution. Evaluating alternatives need not mean wholesale replacement, but could involve incorporating their insights into a more comprehensive framework. Scientific progress often involves synthesizing insights from competing theories rather than simply choosing one victor. Quantum mechanics and relativity were initially viewed as incompatible, yet both proved essential for understanding different physical domains. Similarly, the ultimate cosmological theory might integrate concepts from various current alternatives. The value of alternative frameworks extends beyond their potential correctness to include the questions they raise, the assumptions they challenge, and the new observational tests they motivate. Even unsuccessful theories contribute to scientific understanding by mapping the space of logical possibilities and identifying which observations genuinely constrain theory. Observational evidence contradicting predictions. Beyond the specific challenges already discussed, numerous additional observations conflict with Big Bang cosmology's detailed predictions. These contradictions span multiple domains from large-scale structure to cosmic chronology, creating a pattern of empirical difficulties that increasingly strain the standard framework's credibility. While defenders of conventional cosmology propose explanations for individual anomalies, the accumulation of problems across independent areas suggests systematic inadequacy rather than isolated errors. In particular predictions, the lithium problem represents a long-standing discrepancy between predicted and observed cosmic lithium abundances. Big Bang nucleosynthesis calculations predict the primordial lithium-7 abundance based on well-understood nuclear physics and the universe's early conditions. These predictions are highly reliable for hydrogen and helium, matching observations excellently. However, lithium-7 observations in old metal-poor stores show abundances approximately 3 times lower than predictions. Despite decades of investigation, no convincing resolution has emerged. Proposed explanations involving stellar depletion mechanisms or exotic physics lack definitive observational support, leaving this fundamental test of Big Bang physics unresolved. Lithium-6 abundances create a complementary problem. Big Bang nucleosynthesis predicts minimal lithium-6 production, yet observations of some metal-poor stars reveal significant lithium-6 that appears primordial. If confirmed as genuinely primordial, this excess lithium-6 contradicts Big Bang nucleosynthesis predictions. Alternative explanations involve cosmic ray production or stellar nucleosynthesis, but these mechanisms face their own difficulties explaining observed abundances and isotopic patterns. The lithium problem encompasses both deficit of lithium-7 and potential excess of lithium-6, suggesting either nuclear physics errors in Big Bang nucleosynthesis calculations or problems with the cosmological framework itself. The cosmic radio background presents another puzzle. Observations by the Arcade experiment revealed excess radio emission beyond what known source populations should produce. This excess appears isotropic, suggesting a diffuse cosmic origin rather than discrete sources. The nature of this background remains unexplained within standard cosmology. Proposed sources including primordial stars, early black holes, or exotic physics generally require ad hoc assumptions or fine-tuning. The cosmic radio background might indicate phenomena from the early universe not accounted for in standard scenarios. Anomalous alignments in cosmic microwave background patterns have generated controversy regarding their theoretical significance. Temperature fluctuation patterns at large angular scales show unexpected alignments with the solar system's geometry, called the axis of evil. While statistical significance remains debated, such alignments are unexpected in standard cosmology where fluctuations should display no preferred directions. The patterns could indicate foreground contamination, statistical flukes, or signatures of new physics affecting the early universe. Their presence raises questions about whether cosmic microwave background interpretations are as straightforward as typically assumed. The cold spot, an unusually large low-temperature region in the cosmic microwave background, represents an extreme fluctuation difficult to explain within standard inflation models. While not impossible statistically, its existence is improbable enough to suggest either remarkable luck or physics beyond standard predictions. Proposed explanations include supervoids along the line of sight or exotic early universe phenomena, but none is definitive. The cold spot exemplifies how individual anomalies can be accommodated through special explanations while accumulating anomalies increasingly strain theoretical frameworks. Large-scale structure displays features challenging standard cosmology's predictions. The Sloan Great Wall, an enormous concentration of galaxies extending approximately 1.4 billion light-years, represents one of the largest known structures in the universe. Its size approaches or exceeds theoretical limits on structure formation timescales in standard cosmology. The KBC void, a possible supervoid containing the Milky Way, would represent another anomalously large structure if confirmed. These features suggest that structure formation might proceed differently than standard dark matter simulations predict, or that the universe's matter distribution possesses characteristics beyond conventional models' expectations. Quasar absorption line systems reveal metal enrichment patterns in the intergalactic medium that appear difficult to reconcile with standard galaxy formation scenarios. Observations detect heavy elements in regions far from known galaxies at high redshifts, suggesting widespread early enrichment. The mechanisms transporting metals from star-forming regions into diffuse intergalactic space remain unclear. Galactic winds and outflows provide partial explanations, but their efficiency in distributing metals over vast distances during the universe's first billion years is questionable. The ubiquity of metal enrichment might indicate more vigorous early star formation than standard models predict. The angular size redshift relationship for compact radio sources produces results inconsistent with simple Big Bang expansion. At high redshifts, observed angular sizes increase rather than continuing to decrease as naive expansion geometry predicts. This effect is attributed to light path geometry in expanding spacetime combined with source evolution. However, the quantitative match between observations and theoretical predictions remains imperfect, and alternative explanations involving light propagation in inhomogeneous media cannot be excluded. This relationship provides a potentially powerful cosmological test but depends on understanding source physics and evolution. Supernova data showing cosmic acceleration have been interpreted exclusively through dark energy despite alternative possibilities. Systematic effects like evolution in supernova luminosity functions, metallicity-dependent brightness variations, or dust properties changing with cosmic epoch could potentially mimic acceleration signatures. While extensive analysis has examined these possibilities, the inherent limitations of empirical supernova standardization leave residual uncertainty. Additionally, the assumption that general relativity correctly describes gravitational physics on cosmic scales underlies acceleration interpretations. Modified gravity theories producing late-time acceleration without dark energy remain viable alternatives that fit supernova data comparably well. Gamma-ray burst observations extend distance measurements beyond supernovae, reaching higher redshifts. Some analyses suggest gamma-ray burst data are consistent with acceleration while others find tensions with dark energy models. The heterogeneity of gamma-ray burst populations and limited understanding of their physical mechanisms introduce systematic uncertainties that complicate cosmological applications. However, gamma-ray bursts potentially provide independent evidence regarding cosmic expansion history, and their general consistency with dark energy cosmology strengthens empirical support despite its limitations. Observations of globular clusters, the oldest stellar systems in the Milky Way, yield age estimates sometimes approaching or exceeding the cosmic age calculated from standard cosmology. While uncertainties in stellar evolution models and distance measurements affect these ages, uncomfortably old clusters create tension with the Big Bang timeline. If the universe is 13.8 billion years old, globular clusters containing stars dated to 13 billion years allow minimal time for galaxy formation before cluster creation. This tight chronology becomes problematic if stellar age estimates increase or cosmic age estimates decrease. The fine structure constant's apparent variation with cosmic time, suggested by some quasar absorption line measurements, would indicate fundamental physics changing over cosmic history. If confirmed, This variation would contradict standard assumptions that physical constants remain truly constant. Multiple research groups have analyzed quasar spectra, with some finding evidence for varying fine structure constant while others find no variation. The discrepant results might reflect systematic differences in analysis methods or data selection. Definitively establishing or rejecting variation requires additional high-quality observations and careful systematic error analysis. These diverse anomalies share the common feature of representing observational challenges to specific Big Bang predictions. Individually, each might be explained through special circumstances, measurement uncertainties, or theoretical refinements. Collectively, they create a pattern suggesting that standard cosmology's predictive power is weaker than often claimed. The framework's flexibility allows accommodation of unexpected observations through parameter adjustments or auxiliary hypotheses. But this flexibility itself raises questions about empirical constraint strength. A theory capable of explaining any observation through post hoc adjustments loses predictive power and empirical content. The cosmic microwave background re-examined. The cosmic microwave background radiation stands as the Big Bang theory's most celebrated empirical confirmation. Discovered accidentally in 1965 by Penzias and Wilson, this faint microwave glow permeating the universe perfectly matched predictions for radiation left over from the Big Bang's hot, dense early phase. The radiation's near-perfect blackbody spectrum and high degree of uniformity across the sky provided compelling evidence that the universe evolved from a hot, dense state. Detailed measurements of tiny temperature fluctuations in the background revealed information about the universe's composition, geometry, and initial conditions with unprecedented precision. However, the cosmic microwave background's interpretation depends critically on theoretical assumptions about cosmic history and physical processes. The standard interpretation assumes the radiation originated from electron-photon decoupling approximately 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen. Before decoupling, free electrons scattered photons, making the universe opaque. After decoupling, photons could travel freely, preserving a snapshot of conditions at that moment. Temperature fluctuations in the current cosmic microwave background reflect density variations in the primordial plasma that later collapsed under gravity to form galaxies and large-scale structure. This interpretation requires the universe to have been hot and dense in the past, providing direct evidence for the Big Bang framework. However, alternative explanations for the cosmic microwave background have been proposed that do not require a hot Big Bang origin. Some steady-state cosmology variants attribute the background radiation to thermalized starlight from countless previous stellar generations rather than primordial radiation. While this explanation faces quantitative difficulties matching the precise blackbody spectrum and temperature uniformity, it illustrates that cosmic microwave background observations do not uniquely determine cosmological history without additional assumptions. The cosmic microwave background's temperature uniformity created the horizon problem that motivated inflation theory. Regions of the sky separated by more than about 2 degrees show nearly identical temperatures despite being causally disconnected in standard Big Bang chronology. Light from these regions would not have had time to propagate between them to establish thermal equilibrium. Inflation resolves this problem by proposing that the observable universe originated from a tiny causally connected region that expanded exponentially, stretching to cosmic scales while preserving uniformity. However, this solution introduces the inflation field and mechanism, which remain unverified and theoretically problematic. The cosmic microwave background's temperature fluctuation pattern provides detailed information about cosmological parameters within the standard model framework. The power spectrum of fluctuations at different angular scales displays acoustic peaks resulting from oscillations in the primordial plasma. The peak locations and relative heights depend sensitively on parameters like matter density, baryon density, dark energy density, and spatial curvature. Fitting theoretical predictions to observed patterns determines these parameters with percent-level precision. However, this procedure assumes the standard cosmological model's correctness. If fundamental assumptions are wrong, derived parameter values could be systematically biased regardless of measurement precision. Foreground contamination represents a significant concern in cosmic microwave background analysis. Microwave emission from our galaxy, other galaxies, and intergalactic medium overlays the primordial signal, requiring careful subtraction to isolate the cosmic microwave background. Dust emission, synchrotron radiation, free emission, and other foreground components must be modeled and removed using multiple frequency observations. Residual foreground contamination could bias temperature fluctuation measurements and derive cosmological parameters. Extensive effort has gone into foreground modeling and removal, but complete certainty about the cleanliness of final cosmic microwave background maps is impossible. The cosmic microwave background's polarization properties provide additional information about early universe physics. Polarization arises from Thomson's scattering of photons by electrons in the primordial plasma. The polarization pattern divides into E-mode and B-mode components with different geometric properties. E-mode polarization results from density fluctuations, while B-mode polarization can be produced by primordial gravitational waves from inflation. Detecting B-mode polarization at large angular scales would provide strong evidence for inflation, making such measurements a high priority. However, no confirmed primordial B-mode detection has occurred despite multiple experimental efforts. The BICEP-2 experiment initially reported a B-mode polarization detection in 2014, generating enormous excitement as apparent confirmation of inflation. Subsequent analysis revealed that the signal predominantly resulted from polarized dust emission in our galaxy rather than primordial gravitational waves. This episode illustrates the difficulty of isolating faint cosmological signals from foreground contamination and the danger of premature claims. Current upper limits on primordial B-mode polarization constrain inflation models but have not detected the signal, leaving inflation's direct observational evidence incomplete. Anomalies in cosmic microwave background observations have generated controversy regarding their theoretical significance. The previously mentioned axis of evil alignment, low quadrupole and octupole power compared to theoretical expectations, and the cold spot all represent features that appear statistically unlikely in standard inflation models. Defenders argue that unlikely events sometimes occur and that searching for anomalies in rich datasets guarantees finding some unusual features by chance. Critics suggest these anomalies might indicate problems with standard assumptions about statistical isotropy or inflation's generic predictions. The cosmic microwave background's free streaming length scale, determined by the universe's age at decoupling, sets a characteristic scale in temperature fluctuation patterns. This scale depends on cosmological parameters including the Hubble constant. The scale measured in cosmic microwave background data can be compared with independent Hubble constant determinations, providing consistency checks on the cosmological model. The Hubble tension discussed previously represents precisely such an inconsistency, where different methods for determining cosmic expansion rates produce incompatible results. This tension suggests potential problems with the cosmological framework connecting early universe observations to present-day measurements. The cosmic microwave background's interpretation as primordial radiation assumes that photon-matter decoupling occurred at the predicted epoch and that subsequent cosmic evolution proceeded, as standard cosmology describes. If reionization, the process where neutral hydrogen became ionized by early stars and quasars, occurred differently than modeled, it could affect cosmic microwave background polarization signatures. If exotic physics like photon axion oscillations occurred during photon propagation, it could modify observed spectra or polarization. These possibilities illustrate how cosmic microwave background interpretations depend on assumptions about intervening cosmic history. The Sunyaev-Zeldovich effect, where cosmic microwave background photons gain energy passing through hot gas in galaxy clusters, demonstrates that the cosmic microwave background experienced interactions with matter since decoupling. While this effect is well understood and successfully modeled, it shows that the cosmic microwave background is not simply a pristine snapshot from the early universe but has been modified by intervening structure. More speculative processes might have similarly affected the radiation in ways not currently recognized or modeled. Confidence in cosmic microwave background interpretations requires confidence that all relevant physics has been properly accounted for. The cosmic microwave background provides humanity's earliest observable snapshot of cosmic history, representing invaluable information about the universe's past state. However, interpreting this information requires theoretical frameworks connecting observations to underlying physics and cosmic chronology. The standard Big Bang interpretation achieves impressive consistency across multiple observational features, lending it substantial credibility. Nevertheless, the interpretation's dependence on theoretical assumptions means that alternative frameworks potentially could account for the same observations through different physical mechanisms. The cosmic microwave background strongly constrains cosmological theories but does not uniquely determine cosmic history independent of other assumptions. Philosophical and scientific implications. The challenges to Big Bang cosmology raise profound questions about the nature of scientific knowledge and the relationship between theory and observation. Scientific theories are not simply collections of empirical facts but interpretive frameworks that organize observations within conceptual structures. The Big Bang theory provides such a framework, offering a coherent narrative connecting diverse phenomena from cosmic expansion to light element abundances to microwave background radiation. However, this coherence does not guarantee correctness. History shows that even highly successful scientific frameworks can require fundamental revision when confronted with accumulating anomalies. The concept of scientific paradigms, developed by philosopher Thomas Kuhn, illuminates the Big Bang situation. Normal science proceeds within established paradigms, refining theories and extending their applications to new domains. Anomalous observations initially trigger ad hoc modifications that preserve the paradigm's core assumptions. Eventually, accumulated anomalies may precipitate crisis when confidence in fundamental principles erodes. Scientific revolution occurs when a new paradigm emerges that resolves anomalies while explaining phenomena the old paradigm handled successfully. Revolutionary transitions are contentious because different paradigms employ different concepts and standards, making objective comparison difficult. Big Bang cosmology exhibits characteristics of mature normal science within an established paradigm. The framework guides research, organizes observations, and provides standards for acceptable explanations. Anomalies like the Hubble tension and mature galaxies trigger efforts to modify peripheral assumptions while preserving core Big Bang chronology. Dark matter and dark energy exemplify paradigm-preserving modifications that account for unexpected observations. However, these modifications have grown so extensive that most cosmic content now consists of undetected entities introduced specifically to maintain theoretical consistency. This pattern resembles historical paradigms approaching crisis as auxiliary hypotheses proliferate. The underdetermination of theory by evidence represents another philosophical challenge relevant to cosmology. Multiple incompatible theories can often account for the same observational evidence, making theory choice depend on criteria beyond empirical adequacy. Simplicity, explanatory power, coherence with other knowledge, and successful novel predictions all influence theory selection. Big Bang cosmology scores well on several criteria, particularly empirical scope and coherence with physics. However, alternatives might eventually emerge that match empirical adequacy while offering greater simplicity by eliminating dark matter and dark energy or providing more natural explanations for observed phenomena. The role of metaphysical assumptions in cosmological reasoning deserves recognition. The cosmological principle, asserting that the universe is homogeneous and isotropic on large scales, guides standard cosmology despite being an assumption rather than an empirically verified fact. The principle of mediocrity, suggesting that our cosmic location and epoch are typical rather than special, influences theoretical preferences. These assumptions prove useful in developing tractable theories but could potentially be incorrect. A universe with large-scale inhomogeneity or preferred directions might require cosmological frameworks fundamentally different from current models. Confirmation bias and groupthink affect scientific communities as they do all human endeavors. Researchers invested in particular frameworks naturally interpret new evidence in ways supporting their existing views. Peer review and funding mechanisms can reinforce orthodox approaches while marginalizing alternatives. Careers built on specific theoretical frameworks create resistance to fundamental change. These sociological factors do not invalidate scientific methods but do affect how science progresses in practice. Recognizing these influences encourages epistemic humility and openness to dissenting perspectives. The distinction between successful empirical prediction and genuine understanding requires careful consideration. Ptolemaic astronomy successfully predicted planetary positions through geometric models despite being fundamentally wrong about cosmic structure. Fitting observations does not guarantee that theoretical constructs correspond to reality. Dark matter and dark energy successfully fit numerous cosmological observations but might ultimately prove to be auxiliary hypotheses compensating for inadequate fundamental theory, rather than representing genuine physical entities. Distinguishing successful phenomenology from true understanding is difficult but essential for scientific progress. The Big Bang Theory's cultural influence extends beyond technical cosmology to affect broader worldviews. The idea of cosmic origins from a singular beginning resonates with creation narratives from various religious and philosophical traditions. Some have claimed Big Bang cosmology provides scientific support for theological concepts, while others argue it demonstrates science's capacity to address ultimate questions without invoking supernatural causes. These cultural associations can influence how cosmological evidence is interpreted and how strongly people defend or challenge the Big Bang framework. Maintaining scientific objectivity requires recognizing and setting aside such extra-scientific motivations. The provisional nature of scientific knowledge becomes apparent through cosmology's history. Theories once considered definitively established have been overthrown by new evidence and better frameworks. Newtonian mechanics ruled physics for centuries before relativity and quantum mechanics revealed its limitations. Static universe models dominated cosmology before Hubble's observations forced reconsideration. Present confidence in Big Bang cosmology might someday appear as naive as earlier certainties now seem to us. This recognition should inspire intellectual humility while maintaining appreciation for science's genuine achievements and expanding human understanding. The relationship between empirical evidence and theoretical interpretation illuminates fundamental questions about scientific methodology. Observations do not speak for themselves but require interpretation within theoretical frameworks that give them meaning. Raw data about galactic recession velocities becomes evidence for cosmic expansion only when interpreted through general relativity and cosmological models. Cosmic microwave background temperature measurements become evidence for the Big Bang only when interpreted through hot Big Bang theory. Alternative frameworks might interpret identical observations differently, reaching different conclusions about cosmic history. The possibility of paradigm shift in cosmology raises questions about what evidence would constitute sufficient motivation for abandoning the Big Bang framework. If increasingly mature early galaxies continue appearing, if the Hubble tension persists or worsens, if dark matter and dark energy remain undetected, at what point does preserving the framework through ad hoc modifications become scientifically untenable? The scientific community lacks clear criteria for answering such questions. Different researchers will reasonably disagree about when accumulated problems justify fundamental theoretical revision. This disagreement reflects legitimate uncertainty about proper scientific methodology when facing ambiguous evidence.